Welcome, Shaler area, to note video number 4 in the chemistry unit. This video is going to be about the 4 states of matter and how we move between them. So the first state of matter will be the solid state. This is the state that you think of when you think of any of the stuff you see around you. It's when there is a set shape and a set volume for the substance. And this is because all the particles are all touching each other and they're stuck in place. So the shape's not going to change if you're just sitting there watching it, if nothing's acting on it, and its volume will always remain constant. There's a couple different kinds of solids. We can break solids, the whole group of solids, down into smaller groups. One of them is called a crystalline solid, and this is what your crystals would be made from. And the reason that these things turn into what we call crystals is because there's very repeated patterns going on with the structure inside. If you want to think of salt crystals are made up entirely of sodium atoms and chlorine atoms. And the sodium and the chlorine alternate each other throughout the entire substance. So there'll be an atom of sodium, and then an atom of chlorine, and then an atom of sodium. And in doing so, you end up creating this very specific shape. And actually, in salt, the shape is a cube. You can take a salt cube and smash it, and you'll just make smaller cubes. You can take those smaller cubes and smash them, and you just get smaller cubes. It'll always break into like a cubic shape. Sugar also exists as crystals. They're just not nice, neat shapes like they are in salt. The opposite of a crystalline solid would be an amorphous solid. That seems like a big, strange word, but one of the most important things to learn to do in science, especially when you come across big vocab terms, is break them down. If you understand what the parts of the words mean, then you can get a better understanding of what the entire word means. So morph has to do with your shape or your structure. You can kind of think of that as like the Mighty Morphin Power Rangers. They could change their shape and their structure. And then what happens when you put the letter A in front of a word? When you use the prefix A, what does that do to the word? There were a couple really important science terms from 7th grade, some important vocab terms from 7th grade that did this. The first one you would have come across with would have been sexual reproduction and asexual reproduction. So what's the difference between those two things? Well, in sexual reproduction, you have to have two members of a species both donating DNA, and then that creates a new offspring. But in asexual reproduction, you don't need that. You can just have one member of an organ. You can just have one organism kind of duplicate themselves. There's no mixing of DNA. So it is reproduction without the act of sex. So the letter A, when you use it as a prefix, means the opposite, or not. The other big example in 7th grade was when I was at the end of the year when he talked about ecology. And there were biotic factors in an environment and abiotic factors. Remember, bio means life. So the biotic factors are all the living parts of the environment, and the abiotic factors are all the non-living parts. So in this example, amorphous means solids without a good structure. And these are going to be things like your plastics, your glass, and your rubber. So crystalline solids have nice repeating patterns. Amorphous solids, far less regimented. The second state of matter, the liquid state. Liquid is a fluid. You're going to see this term show up a lot. A fluid is any substance that can flow or move about. So a liquid is a fluid state of matter that has a set volume. You can't change the volume of a liquid. You can't squeeze it, in other words. And that's how hydraulics work. If you have liquid all the way through a tube and you push on it, you get the same amount of force out the other side of the tube. It's how the brakes in your car work. You press on the pedal of your brake pedal, it pushes on the fluid pushes on the brakes on the wheels. You don't get any sponginess going on in there. The exact pressure you push on is what comes out the other end. The shape, though, can change, and the reason the shape can change in a fluid is because these particles aren't stuck in place like they are in a solid. They're a lot more mobile. Now, they can slide around each other, but they still are touching each other. So the molecules or the atoms are still in constant contact, but they're able to move about. Now you can get like spaces in between. So like these are all touching and you still have this little space in there. That's where the things go when you say dissolve stuff in water. like the salt or the sugar molecules can go and kind of hide between the liquid molecules when you dissolve things. There's a couple of phenomenons or a couple of vocab terms you should know about when it comes to liquid. One is called surface tension. Surface tension is what happens at the very edge of the boundary between the liquid, we'll say this is like a pond or a lake or a swimming pool, and the atmosphere or the gas. So the boundary between the air and the water, you get this special kind of phenomenon, especially with water, because water molecules are attracted to each other. Water molecules, because of their shape and the kind of bonds that they're made from, have a slightly positive side and a slightly negative side, and that causes them to be pulled towards each other, sort of like tiny little magnets. And that's what gives water a lot of its really unique properties that other liquids don't necessarily have. But where it shows up in surface tension is that the molecules right on this boundary are even more attracted to each other than the ones down here, because they're only being pulled sideways, because the air isn't, like, there's no attraction between the water and the air. So that's really strong in this direction, and it gives the top of the water this sort of like a skin layer. It makes it harder than the rest of the liquid. And you can feel that if you do like a belly smacker into a swimming pool. But if the water is choppy and wavy, then it doesn't hurt so bad, because that surface tension is kind of broken up. You can put things in water too that kind of break up the surface tension as well. Like any kind of detergents or oils will break up the surface tension. When I was a kid, I used to have to paint docks. I grew up on a lake, and one of the things I would do in the summer would be paint people's docks. So I'd be out in like waist deep or chest deep water painting the dock that they would hook up their boats to. And there'd be all kind of bugs and spiders and things like that running around on the water, because they can do that because of the surface tension. You can get these bugs that don't weigh enough to break through that like hard layer that's made by the surface tension. But whenever a drip of stain would like fall off the brush and hit the water, it would totally destroy the surface tension properties, and the bugs would all just instantly go through and sink. There's a neat thing you can do. I've seen it done with like a needle that you would sew with. If you put it on a Kleenex and lay it on top of the water, the Kleenex will absorb the water and sink. And the needle will sit there and float up on top of the water. It helps you put a little bit of wax on it as well. But that's an example of surface tension. So the other vocab term that you need to know when it comes to liquid is viscosity. Viscosity is a liquid's resistance to flowing. So how easily do the particles slide around each other, in other words. This has a lot to do with the size of the particles and the shape of the particles in the liquid. So if you're talking about like little tiny round particles, like with water, they're kind of round, then they can slide and roll around each other very easily. But if you're talking about like long strings, or especially if things have branches on them, as far as a molecule goes, they will easily get tangled. It'd be the difference between having like a bucket full of bouncy balls rolling down a ramp versus a bucket full of coat hangers trying to slide and roll down a ramp. They'll very easily get caught on each other. Or like holiday lights, when you pull them out of the boxes that you have them stored in, they're always all tangled around each other. They're not going to slide around very well. So things that are made of molecules that get caught on each other have a very high viscosity, and they're very, very resistant to flow, and they're going to flow much slower. So here are 4 pictures of motor oil. Whenever you go get motor oil for a lawnmower or a car or whatever, you'll see this SAE number. Now, if you talk to people who work on cars, they tend to call this the weight of the oil. But as you know, we often use words incorrectly. I wouldn't call this the weight of the oil. It's much more the viscosity of the oil, or even you could even get away with saying the thickness of the oil. And in here, they drop down some ball bearings into these test tubes, and the higher number is a higher viscosity, and it takes longer for the ball to get to the bottom. Over here we have different liquids all being poured at the same time. This one's flowing very easily. Over here we have more like gels that are going to flow a lot slower. So they have a much higher viscosity. The third state of matter we're going to discuss is the gas state of matter. And gas is also a fluid. As I said, that word's going to keep coming up. People tend to think of fluids as liquids because you can see them flow, but gases flow as well. The particles can easily move around each other. Now, the difference between a liquid and a gas is that while a liquid has a set volume but no set shape, you can pour it into a round container and that liquid becomes round. You pour it into a square container, the liquid becomes square. Gases have no set either. Gases can be any shape of a container you put them in, and they will expand and fill any volume of a container you put them in too. You can squeeze a whole bunch of gas into a little container, or you can put the same amount of gas into a big container, and the space between the particles will just get bigger, and they'll expand out. The biggest difference between...
Pardon for the interruption, but...
Sorry about that. I kind of forgot what I was saying, though. The biggest difference between a gas and a liquid is that you have space between the particles. When in the liquid, all the particles are still touching, but in a gas, there's open space. And that's what makes it a really good insulator, because they're not directly touching each other, so if that thermal energy needed to go from one to another, it would need to travel a slight distance before it could do that, and that slows down conduction. A fourth state of matter. There's more than just three. You're probably only familiar with the solid, liquid, and gas, but plasma is another state of matter. And it's like a superheated gas. It's a gas that we have added a whole lot of energy to, and it causes interesting things to happen to the molecules. On the other side of the spectrum as well, you can take a solid and slow it down even more, and the particles become even more solid, more extreme on the solid side, and that's called Bose-Einstein condensate. But we're going to talk about that one in this class. But the plasma is another fluid, and it's a fluid state of matter that's like a gas that has been super energized. So here, we'll just call these hydrogen atoms. Remember, hydrogen gas itself would be H2, just like oxygen gas would be O2. So these are just hydrogen atoms, but they're in a gas state because they're separated from each other. We have a nucleus with a proton in the middle, and we have a single electron going around the outside. Well, if we take that and we energize it, the energy goes a lot into the electrons. The electrons start going so fast around this core middle nucleus that they fly off and they're no longer connected to the nucleus. Now they're all on their own, and the electrons are just kind of going around, and the nucleus and the protons in the nucleus are also going around, and they're separate from each other. The really interesting thing that comes from this is if you look over here, it's impossible to get two protons to touch each other, because there's electrons in the way. That's when we do chemical reactions, it's the electrons that are interacting with each other. The nuclei don't have they don't even come close to each other even in distance. But when you put it into a plasma form, now you can actually get interaction between the protons and between the nucleus of different atoms. And then you get really interesting things. That's what happens in a star. So anyway, plasma is a fourth state of matter. It behaves different from a gas because these electrons are all flying all over the place. And since it is what stars are made from, it's the most abundant form of matter in the universe. I always get students ask on the first quiz what the word abundant means. Abundant means most or a lot. There's a plethora of material. There's a lot of it out there. You don't have to worry about running out. The most abundant form, because most of the matter in the universe is in stars. If we just look at our one solar system, something ridiculous, I don't know the exact number, but like 90% of the matter in our solar system is in our star. And if that's the same for all solar systems, then 90% of the matter in the entire universe is then found in stars, and which would mean it's in the state of plasma. All right, I have a video here to show you where you get to see some plasma. Hold on, there's a guest at the door. All right, sorry about that. I had a guest at the door. Someone came to tell me that they found a mistake in the calendar. All right, here is a video about plasma.
So today I'm at the University of Sydney with Steve Bosey, and we are exploring everyone's favorite state of matter, plasma.
Well, actually, my favourite state of matter is the Bose-Einstein condensate, but that's just me.
That's for another episode. So for now, we are trying to replicate these videos that you can see on the web where people use a simple grape and a microwave to produce plasma.
We took a grape and cut it part of the way through, so you have two halves with a tiny little isthmus of the grape skin holding the two halves together. Put that in the microwave oven now. Try to prop that up so it's sitting in the middle.
All set.
Is this going to be dangerous?
I don't think so, but we are experts, so Be careful if you're trying this at home.
And bingo.
Where's the plasma? Whoa! There's the plasma.
Hey!
Wow, well that was some pretty amazing plasma that we made in this microwave. What is plasma for people who don't know?
Okay, if you take a gas and you put lots of energy into it till it gets very hot and the particles are very, very energetic, you start to rip electrons off the molecules. So you end up with a soup made up of negatively charged electrons mixed in but moving freely with a bunch of positively charged air molecules.
And why does that give off light?
Well, anytime that you put energy into atoms and molecules, the electrons start moving around, changing orbits and that kind of stuff. So anytime the electrons are being excited and de-excited, you're going to get light. Whoa! Who needs...
And we also imagine that it's very hot, so it would be glowing white hot anyway.
Yeah, possibly also some of the ingredients in that plasma have actually been heated up very high, so they're incandescent. They just glow because they're hot.
Okay.
Don't know.
So what did we find worked the best with microwaving our grape? What lessons did we learn?
Okay, first thing we discovered was we got better results if we dried the grape up before we put it in. We found too much water gave up too much steam, and they tend to extinguish the plasma.
And then Steve came up with a great idea of actually cutting the grape completely in half, but using these dangling flaps of grape skin.
And grafting them together, just laying them over the top of each other.
And that seemed to work better because we could have reduced the volume of the grape, and that seemed to help.
Yeah, because we used smaller pieces of grape, so we had less steam, also less thermal mass, and possibly less grape absorbing less microwave energy, so we got higher fields.
Oh, yes.
Feces.
Oh,
yes, did you see that fireball? That was an example of multiple plasma.
And then, of course, the trick was to try to capture the plasma so that we didn't do damage to the microwave, for one thing, and second of all, so that we could observe it quite nicely in a container. But we had trouble with the glass that we were using, a few glasses. We couldn't seem to get it to work.
The guess is that the glass was absorbing too much of the microwave energy, and so we weren't getting the very high fields you need to make the plasma. Oh, yeah. Oh, no.
So we moved over to a plastic container, which seemed to do much better.
Yeah, if you can just tolerate the fact that the plastic container melted afterwards. Plastic container to capture the action and adventures. Look. Go the laws of physics.
Yeah.
Oh, yeah. It's still going. Go the laws of physics.
Yeah.
Oh, yeah. It's still going.
Do you smell that? Is that a new smell? Is that a melting plastic?
Are you still filming?
Oh my God.
Catch that. Look, it's got a smile. Even the container's got a smiley face after that run.
Yeah, it was only like a one-hit gig. So what sort of future investigations would you like to do here?
Okay, now, in order to understand exactly why this happens, we really need to be able to control the variables inside that grape. Okay, we can't control the ingredients of the grape; they come to us as is. So what we'd like to do is make an artificial grape. So we, get cotton balls. We can put conductive liquid in it. We can put salty water in it. We can put grape juice and control the volume of these things. So one by one, we can actually nail down the different variables, and we'll have to find some artificial skin to replace the grape skin. I don't know if it has to be grape skin. Maybe a wet piece of paper might do the job. I don't know.
Okay, so you should look forward to that on another episode of Veritasium. Care for a grape?
Thank you very much.
Physics is tasty.
Holy! Oh, see, what did I tell you? What did I tell you? Oh! But wait, there's more.
No, I think that's it.
Alright, I hope you enjoyed the video. All right, let's see here. What is next? All right, so we have these 4 states of matter. Well, we can move matter between them. So if we go from a solid state to a liquid one, we call that melting. So melting is anything that goes from a solid state to a liquid one. It's not just when water does it. And the reason that things melt is because in the solid, the particles are all fixed in place. But as you heat them up and heat them up and heat them up, and they start vibrating faster and faster and faster, they break loose from each other. Even though they're still touching each other, they're no longer kind of locked in place, and it allows them to be able to slide around. And that's the difference between a solid and a liquid. Now, a material it'll stay the same temperature the entire time while it's changing state. So if you look at those phase change diagrams, the graphs that we'll be seeing a lot, where it goes from it's the solid at the bottom, and then it shows it melting, and then it's a liquid, and then it shows it evaporating, and then it's a gas. The moments where it is changing state, the temperature line is always going to be horizontal, because the temperature doesn't go up and down. If you have boiling water, well, that boiling water is going to stay at one temperature until it's all boiled, much like the melting ice. That ice is going to be the freezing point of water. It's going to be 0 degrees Celsius at 32 degrees Fahrenheit the entire time that ice is melting. So it stays one temperature until the whole thing melts. Freezing would be the opposite of melting. That's whenever you go from the liquid state to the solid one. And again, we have a freezing point. That would be like the freezing point of water, would again be 0. It's the same as the melting point of water. It just depends on what direction you're going, if you're heating it up or if you're slowing it down. Now, the interesting thing about these phase changes is what happens with the energy when it's going on, because it seems to be a little counterintuitive sometimes. So the act of freezing actually gives off energy, which if you were to just think about it, you would think that freezing things are getting colder. So it would be kind of pulling in coldness, but remember, coldness isn't a thing. So what's actually happening to the particles in the matter is that the particles are slowing down, right? They're slowing down, they're getting in more fixed positions, so there's less thermal energy in them. Well, we can't destroy energy, so that energy has to go somewhere. So if they start with more energy and end up with less energy when it's done, that energy had to leave the system. So when things freeze, they give their energy off to the air around them. So they actually give off energy. Great picture of water freezing in a really, really cold environment. Go out with a bucket of water when it's like negative 20 degrees outside, Fahrenheit, or Celsius, but that'd be super, super duper cold. I don't know if there's any places on Earth that actually do that. Throw it up in the air and it just freezes instantly. Vaporization is what we call it when something goes from a liquid to a gas. So this happens whenever you add even more energy to the liquid state, which has things moving around each other already, but now they start vibrating and moving around so fast that they separate from each other. When they separate from each other and leave that space between the molecules, now you have a gas. And there's two kind of subcategories, or two types of vaporization. One is called evaporation, and this happens at the surface only of a liquid. Because you can have things evaporate even if they're not really hot. You know, you pour water down on a table and come back after a couple hours and it will have evaporated. And that's because there's some interesting things that start going on with individual particles in the liquid, and they start to kind of break free and move into the gas. It's almost like they're dissolving into the air. The other way of vaporization is boiling. Now, boiling happens throughout an entire liquid, and that will happen, you know, if you heat water up, you'll get these bubbles appearing inside the liquid. They form at the bottom, and that's the liquid water turning into gaseous water and then working their way up to the surface. There's a big thing that has to do with change of state also that deals with pressure, but we'll talk about that in a little bit. I guess we'll talk about that right now. So It depends a lot on pressure. If you have a glass of water and you put it in a vacuum chamber and you take away all of the air pressure, even though it could be very, very cold, it will start to boil because of the vaporization pressure. Now, we can look at this just a little bit here and see the impact of air pressure a little bit just by changing from, say, sea level up into the mountains. So down at sea level or right on the beach, like if you go over and you start boiling water at, like, you know, if you go down to Florida and go to Daytona Beach or something like that, the water will boil at 100 degrees Celsius. That is the boiling point of water. But if you go up to Colorado, if you're over in Denver and you're cooking and trying to boil water, it won't boil. It'll boil before it gets to 100 degrees Celsius because there's less air pressure because you're up higher in the atmosphere. Instead, it'll boil at 95 degrees Celsius. This has a really big impact on cooking, right? If you're trying to, say, hard boil an egg, it might take, it might take 5 minutes to hard boil an egg at sea level, but up at in the mountains, since it doesn't get as hot, since that water can't get any warmer than 95 degrees, it takes longer to cook the food. So if you ever look at recipes, sometimes it'll have a high altitude version of the recipe, and it always changes the cooking temperature and the cooking time on it. So vaporization absorbs energy the same way that freezing gave off energy. And this is why sweating lowers your body temperature. That's why when you get hot, you sweat. Your body will kick some of the water out onto your skin. It's actually the makeup of the chemicals in sweat are identical to the makeup of the chemicals in urine. It's water, it's salt, and it's urea. In urine, it's just a much higher concentration of urea. But that's why when you sweat a lot in your clothes, you get, that body odor and your armpits will turn yellow. That's because it has the urea in it. You're literally like kind of peeing through your skin. But when the water evaporates off of your skin, it takes a lot of that energy with it. It absorbs the thermal energy from inside your body into the liquid that heats up and starts making the particles move faster. They turn into a gas, and that energy leaves your body with the gas. Condensation is the opposite of vaporization. That's when the gas turns into the liquid. And that happens whenever the particles of the gas slow down, that open space that they have between the particles collapses, and now the particles are touching, and then it goes from a gas to a liquid. Now, one important note here, because people often, especially students, often kind of mess this up. They look at boiling water, and they see the steam coming off the water, and they think that that's water vapor, and that's just totally wrong. Gases are essentially invisible. There's space between the molecules, and we can't see molecules. So if we have space between the molecules, we definitely can't discern individual molecules. So when something is in a gaseous form, it is pretty much invisible. There are some gases that'll have a color to them, like chlorine gas can kind of look a little like yellow-greenish to it, but in general, gases are completely invisible. So if you can see something, you're not looking at the gaseous state. In the case of steam, for example, in water, you're actually seeing micro droplets. You're seeing really tiny particles of liquid water that are floating in the air because of the hot currents of air that are going up. So whenever you are looking at steam, at like the steam part, or what you might call that, you're actually looking at really tiny liquid phase of water. You can't actually see water vapor. Another way that matter can go from one form to another is via something called sublimation. Sublimation is when you skip the liquid phase and you go directly from the solid to the gas. And there's a bunch of materials that will do this. And this happens when the particles along the surface of a solid, instead of breaking away and breaking loose and sliding around each other, they jump right to having open space between them. And they go right from the solid to the gas. This may seem kind of crazy and foreign to you, but things around you do it all the time. It's how air fresheners work. This is something called mothballs. It's also called the actual name of it is called naphthalene. And I remember whenever I was a kid that all of like my grandparents' houses, and if I would go into like an older person's house, you would always smell mothballs. And it's because you could put them in your closets and things like that, and bugs hate the smell. And they just look like these white balls that eventually just disappear. They just kind of shrink and shrink and shrink until there's nothing left. Bugs hate the smell, so it keeps the pests out of the house. We kind of make houses a little bit better than we used to, so it's harder for the bugs to get in, so you don't see this quite as often. I think they're actually called mothballs because people put them in their closets, because there was a problem when we would have bugs in our houses that the moths would eat the sweaters. You would eat holes in your sweaters while they were in your closets. And you go to wear your sweater the next winter, and it suddenly would have a bunch of holes in it. Well, people would throw these in the closets to keep the moths away, so they called them mothballs. This is dry ice, which is the solid form of carbon dioxide gas. Carbon dioxide doesn't really exist in a liquid state unless you make really specific conditions, but in a normal kind of out in the atmosphere of Earth, you can't get liquid carbon dioxide. It'll go right from the solid right into the gas. Now, this stuff around it is not the gaseous carbon dioxide, because again, you can't see a gas. What this is the fog. This is where the air gets so cold because of the dry ice that the water molecules in the air that are in the water vapor form condense together to make little droplets of water, and that's what you're seeing here. These are like micro little droplets of water. You could call it fog, because that's what fog is. Fog is just a cloud that's touching the earth. So all of the other ones had opposites, and so does sublimation. You can go right from a gas to a solid, and that's called deposition. And that's how frost and snow forms. So this is whenever you have the vapor form, you have the gaseous form of something, and then they come together and touch, but instead of coming together and touching in a liquid form, they are instantly locked into place. So now we have a solid. Now this is a very exothermic change of state, which means it gives off energy. It's not a chemical reaction, exothermic, but it gives off energy, and it gives off a significant amount of energy. If you're ever outside, it can sometimes be really cold in the winter, and then it starts to snow, and it'll feel like it's warmed up a couple of degrees, and that's because it has. The act of actually creating the snow via deposition warms up the area, because all of that extra energy that was keeping the vapor form of the material, the vapor form of the water, and now it's locked down into a solid all of a sudden, and all of that extra energy just goes off into the air and warms the air up. This is a real phase change chart for water. It shows all of the different possible combinations of pressure and temperature in what phase the liquid will be in. This is the kind of chart and graph that you'll see on things like the PSSAs. The PSSAs are really infamous for showing you overly complicated charts and graphs and then asking you relatively simple questions about them. So when you do come across something like that on a test, don't just skip it out, because you're like, oh, I can't understand that. Take a look at it, look at the question, find the information that you're looking for in the question, and forget about all of the extra stuff that's in the chart. It's really good advice for the science PSSAs. All right, they are all written in ways that you can answer them, but they just look more complicated to you than they really are. So here, a couple things to know before you try to read this for the quick check questions. Things you may not know ahead of time. Pressure at sea level is 100 kPa. Well, PA is pascals, K is 1,000 pascals, so they're kilopascals. So 100 kilopascals is the same as 1 bar of, what they call that mercury, it's 1 bar, and that's also what we call 1 atmosphere, and that's normal air pressure. That's air pressure that you're used to feeling, and that's this line right here. So we have 1 bar of pressure, which is exactly equal to 100 kPa over here, and it's 1 atmosphere. That's where when we talk about things freezing and boiling and stuff like that, we're always talking at this level. That's normal. And then as you heat things up or as you increase pressure and things like that, you get up here, and the other word on here is critical point, and that's right over here. All right, this is the critical point. This is the temperature and pressure combo, where once you get beyond that, you can't tell the difference between liquid and gas. They just kind of become a single thing. So see if you can use this chart to answer the quick check questions that we'll have in class. Notice we have pressure on the y-axis. They're exactly the same pressures, just measured in different units. And the x-axis is temperature. Down here we have Celsius, and up here we have Kelvin. So they're exactly the same temperatures. They're just on the top and the bottom of the x-axis. So good luck, and I'll see you in class with your quick check answers. Booby trap coming. 22 questions about phase changes and states of matter. Thanks for sticking around.